Professor Pradeep to share his scientific thoughts and ideas. And I think no introduction is needed. For last 27 years, he is in IIT in Madras. Now he is an institute professor there. And we know that he discovered advanced sustainable and affordable nanoscale materials for removal of toxic contaminants from water. And over 1.3 million people are benefiting this all over India. And in its hand over 125 patents, including in US. And his nation honored him with S.N. Bose Award, and in 2022 with Padma Shri, a prestigious award by nation. And about his publication, he had more than 500 articles. He had written several books, and 30,000 high index. It is over than 30,000, and with immense pleasure, I invite him to deliver the talk. Thank you.
Okay. Yeah. It's always a pleasure to come to my alma mater and talk about science. This particular subject matter was not covered here in this detail, and therefore I thought of choosing this subject. Those of you who are standing here and all, I would like you to occupy the seats. In case there are not enough seats, please get some chairs. And please don't move around, okay? All right. Okay. You might be wondering why this subject or this title, Atomically Precise Matter, because chemistry is always atomically precise. We say H2O, it is atomically precise. Atomic precision is central to chemistry. And therefore, matter is atomically precise. So why is that a new title, Atomically Precise Matter? So that is because today we have objects of this kind, which are new forms of bulk materials that we know of. The bulk material is a piece of gold that you take, cut it into pieces. That piece is not atomically precise, because the next piece can have a different number of atoms. Today it is possible that we can have atomically precise pieces of matter, giving you bulk matter. Now, that subject is expanding tremendously, and that subject broadly is classified as atomically precise cluster materials, or atomically precise cluster assembled solids. And this subject, in the past few years, has attracted a lot of attention. One of those building blocks of that atomically precise cluster assembled solids, the precise piece of that assembling material is atomically precise cluster. One of them is represented here. So this is a piece of gold, 25 atom piece of gold. It has several ligands around it to protect this piece of matter. And without this piece of, without this protection, this 25 atom gold or 25 atom silver or 25 atom palladium or platinum can all be made. However, they can be made only in the gas phase. And if you make this in the solution phase, the molecules of this solution, like water, will react with it. Because these atoms on the surface, I can't use this pointer, atoms on the surface can all be very reactive. So therefore, this 25 atom piece of gold or 25 atom piece of silver can be made in the gas phase in an isolated form in vacuum without oxygen, without water, without ammonia, without all the molecules. Now you can study that. That subject area was active for a long time and continues to be active to a limited extent even today, called gas phase clusters. But today, with synthetic chemistry, you can make that in solution. You can make this in solution. Why don't we run this timer? So we are probably we have used some 3 minutes, 4 minutes, I don't know. Yeah. This may work on it. Okay, great. Thank you very much. So we have these atoms which are all, let us say, imagined to be unprotected in the gas phase, in vacuum. They are stable. But in solution, we have synthetic methods today which will allow you to make this very same entity with protection. And these protecting molecules are called ligands. And they are shown here in detail what they are and all. In the course of this lecture, we will talk about. Now, this is 25, but then similarly, there can be silver 25. There can be other clusters as well, like 29, or there can be something called 44. This is something that Francisco Schillaci was involved in the beginning, the very early paper of this. And Osman Bakr was involved in this. So there are several people. Well, I don't want to tell all these names right now. But this is having a very sort of unusual structure. This is built around what is called a hollow 12-atom icosahedron and protected with another set of atoms. So it is a 20-atom another shell protected with another 12 atoms. So 12, 20, 12 will make 44 atoms of silver, and then protected with ligands, which are shown by these yellow fellows. These are sulfur atoms, and these are carbon atoms. Hydrogens are not shown here. So that makes this particular entity. People subsequently, after that original work of Francisco and Osman, this was then subsequently crystallized by these fellows and solved the crystal structure. So today, this subject is very big. This is a small cluster, large, etc. These clusters today can be put in a mass spectrometer, so we know precisely what the composition is from something called the mass spectrum, and I am showing you mass spectra of all of these three things overlapped in one spectrum. Now, this subject is expanding because you have mass spectrometers which can measure larger and larger masses. Today's mass spectrometers, you know, mass spectrometry was started in 1912, and then we have already celebrated its 100th year. Many mass spectrometers have come. Today we can measure the mass spectrum of a virus. We can measure mass spectra up to 50 million Daltons, or even beyond. So this kind of mass spectrometers are available. Some of them are available in our laboratory. So these are all our data. Okay, so we make all these clusters. Now, as the subject area is expanding, we write reviews, right? We write many articles. And you see, this is a 2017 review. So this area is expanding. Lots of people are working on this. But I must tell you, chemistry that I just told you, the atomically precise pieces of silver or gold or platinum or nickel, this we can do in the laboratory. you can also do this atomically precise synthesis with carbon. So this is a friend of ours. This man is in University of Tokyo. He makes precise carbon nanotubes by assembling atom after a carbon atom, one after another, and creating structures. What does that tell you? Well, you must have heard about from your textbook, vitamin B12 was a great synthesis, right? Woodward did this great synthesis, and for which he was awarded a Nobel Prize. Now, today, that vitamin B12 kind of complex chemistry can be done to build nanostructures like that. You must have heard that some of the nanotubes can be chiral. So you can synthesize chirality. You might have heard that this yellow fellow can be electrically conducting. You can synthesize electrically conducting things or electrically insulating things. So all of these can be done by precise chemistry. So what does that tell you? It tells you that you can create the entire periodic table. You can have atomically precise materials across the periodic table. I showed you a few things here, but I showed you one example here. But there are friends of ours who make nanoparticles of all these. That means you can also do clusters of this entire periodic table. So you must wonder, or you might be wondering, why at all this Professor Pradeep is working on these atomically precise particles? One single sentence answer that I can tell you is atomic precision is essential for sustainability. If you want to utilize materials for purposes such as CO2, storage, conversion, create more energy, or do catalysis and whatever, you require materials, which may be catalysts, which may convert one molecule to the other. In that process, catalysts are made with elements like platinum. You can't go and create platinum. You have to live with the platinum that the nature has been, given us. So this platinum is limited. The resources are limited, and therefore it is important to use as minimal a quantity as needed. One way to do that is to use smaller and smaller particles, and therefore atomic precision is essential for growth. So sustainability requires this, and there are very many other reasons that I can illustrate to you. If you are interested in, we can discuss this more. I showed you a few clusters, but it is possible to synthesize very large clusters. People have synthesized clusters as large as 900 atom gold with atomic precision and measured the mass spectra of those. And today's mass spectrometers are very high-resolution instruments. And I showed you one high-resolution spectrum before. So this high-resolution spectra, all these peaks are due to what are called isotopically resolved mass spectrum, people say. And that is because that is giving you a fingerprint of the composition. And from that composition, you can calculate the mass spectrum, and you can fit that mass spectrum, and that is what is shown here, which tells you precise composition. So when you make these, when you have atomic precision, it is possible that you can crystallize such entities because they are molecules, like the molecules that Professor Murugavel will show in his lecture. So if you do that, you can get crystal structures. And I like the crystal structure that I showed you previously of Ag44. This is a crystal structure of Au25, just that the complex ligand that I showed you earlier, I have reduced that. The entire hydrocarbon chain has been reduced to just a methyl group. But you see the beauty of the structure. This beauty is built around, or that includes this icosahedron, one atom at the center, 12 atoms outside, and then there are some pieces of what are called staples, some staples, and such structures make this beautiful entity. Today, I showed you atomically precise matter. So this matter that you have is atomically precise, composed of these atomically precise clusters, and in very many ways you can build this. So why are we talking about this? So when a molecule like water is there, you can have all its properties. In fact, water's properties can be very many. You can write a book just by listing out the properties of water. So this is one such, a small collection of water's properties. So similarly, the cluster AU25, some ligand 18, can have properties like molecular formula, molecular weight, molecular structure. All these are standard aspects of a molecule which characterizes that molecule. You can have properties such as molecular absorption or emission, molecular reactions, molecular assembly, molecular co-crystals, ionization potential, electron affinity. You see many other things which are all not known about these clusters. It is also possible that you can study their phase behavior, phase transitions, physical properties, mechanical properties, and very many of them are not known. So therefore, those of you sitting in the audience, if you are interested in, the subject area is open. Now I showed you about one cluster, one particular AU25. There are very many. It's not just gold, as I told you. The entire periodic table is open. You know, organic chemistry, with so many years of work, with just one element carbon, people have made over 8 million molecules. So likewise, you have very many molecules, clusters that can be made in the years ahead. So we have written a book on this subject area. A lot more things are possible. So I'm going to show you one example, just one aspect of that, and then tell you why that is important to address the larger problem of sustainability. So you know, these clusters are soluble entities. I told you that something can exist in gas phase, but you can make it in solution now with ligand protection, and they are stable, and they can be crystallized. These entities sitting there, these molecules that are making the solution can be crystallized. If you take a photograph of that in visible light, this is what you get. But you can irradiate with ultraviolet light, but this cluster then emits this particular red light. So this is called luminescence. But today we know that this luminescence is actually fluorescence. Luminescence can be fluorescence or phosphorescence, but as far as this particular cluster is concerned, it is fluorescence. The difference between this you can study in your textbook. So I was asking this question. You have this molecule in solution. Let us say we have another molecule, another cluster in the solution. Just as you have studied chemistry, A plus B, is it possible that clusters can also do A plus B reaction? And this is quite unlike reactions that are happening on the surface of these clusters or nanoparticles, as Sebastian Peter would tell you, which are called catalysis. They don't convert the cluster or the nanoparticle, but here the nanoparticles themselves participate in the reaction, the chemistry, and that builds new chemistry. And if these are molecules really, the molecules should show reactions. How do you study these reactions? These reactions can be studied by spectroscopy generally. We decided to study this with mass spectrometry, but equivalent thing is possible with other spectroscopic techniques as well. Now, when we started doing this in 2000, somewhere around 2015 or so, we wrote this paper in 2015, it was published in 2016. So we said A and B, let us say they are two different clusters, like here, two different clusters. Can they show reactions to give you C and D? Okay. If that is possible, then very many A's and B's exist, so all of them should show reactions. If they are molecules, there must be a way to make them react. Okay? If they react, there must be a reaction mechanism. If they react, there must be a reaction thermodynamics, some enthalpy and some entropy. And if that is so, there must be some kinetics associated with this process, some K1s and K2s and all that. Then there must be some dynamics associated with that. So we did all that. So that's a long story. I can't tell you all that. But just to tell you that if they are molecules, they must show molecular reactions. So how do you do this? Imagine you have this molecule, which is now protected. 25 is protected with fluorothiophene, which is this entity. And you put this on 25, the H, those of you who know this chemistry, H goes away, and this S binds with gold. So that is the entity that you have. So this entity has no H there, and that is what you see in the mass spectrum. So if you measure that mass corresponds to this entity minus 18H. Okay. It also fragments to give you some peak like this, Au25 FTP18. But you mix this with this. You get another peak corresponding to this entity, which appears somewhere here. The mass is somewhere higher. Actually, I'm not showing you. So if you react this, or if you mix this two, suddenly a peak comes up. Another peak, many peaks come up. What is this? This is the difference between the masses of gold and silver. Gold is 197, silver is 108. You must have studied an average mass of silver is 108. Silver has two isotopes, 107 and 109. Nearly 50-50, the average is 108. So that's taken as the silver mass. So the difference is, this peak is then that Au25 minus 1 Ag1 FTP18. So this can be 2, 3, 4, 5. Correspondingly, some fragments also show up. This is just after mixing 2 minutes. Wait for 5, 10 minutes, this peak goes down in intensity. Wait for 1 hour, this peak disappears completely. And a distribution comes up. So what we have done is molecular reactions in which atomic substitution has happened. So keeping the same nuclearity, which is the number of atoms, the same, you have substituted gold atom with silver atom. Correspondingly, this substitution also occurs that appears in this another region of the mass spectrum, which I am not showing you. Okay, why do they react? Well, we asked this question computationally. And we asked the question, where exactly in the structure that I showed you before, where exactly you have the atom substituting? So if you have gold 25, and if you put a silver atom, will that silver atom sit here? Will it sit here? Will it sit at the center? These are the 3 possible positions. And after sitting there, let us say one more silver atom comes there. Will it sit? If one of them sits here, the next one, will it sit here or there, or where does it sit? So you can study all that in great detail computationally. Sum and substance of the story is that this reaction occurs because of thermodynamics. So this substitution occurs because of thermodynamics. Now there is entropic contribution, there is enthalpy contribution. So you ask the question then, how does the chemical bond open up? Just as organic chemistry reaction mechanisms, you can write reaction mechanisms for this? Well, so we studied that in great detail. So let us say, imagine this cluster and this cluster now, if you do a reaction now. Okay, now you can do this cluster and this cluster are mixed together. This is gold cluster, which has no silver in it. Therefore, I have written it as 0, 25. This cluster has no gold in it. Therefore, I have written 25, 0. Okay, very nice. It has more ligands and all, which are not represented here. Just after mixing, these peaks come up, and I showed you the reasons for it. Just after mixing, these peaks come up. But this region appears silent, but it is not silent. If you expand it, you get a number of peaks. These peaks are due to various substitutions, and these peaks are larger in intensity because total enthalpy is not the only contributing factor to free energy. There is entropy also, delta G minus T delta S. Delta S is greater for these substitutions. Larger number of gold and silver substitutions, you have these. And therefore, these peaks are larger in intensity. Now, you will be seeing, for curious eye, if you take an equimolar mixture of A and B, this intensity and this intensity should be equal. But they are not equal because this fellow has a lesser ionization cross-section in comparison to this. So there are more reasons, and there are more details in this spectrum. I'm not going into that. So let us say there is a cluster, there is another cluster. They come together, and atoms are now exchanging. How can atoms exchange if these clusters cannot form what is called a heterodimer? They come together and interact, then atoms should exchange. Okay, can we see this? These atoms, when these clusters come together, they form a dimer, and you must observe this. So this is that dimer in the initial stages of reaction, which you can't see here, but you expand it. This is what happens in the very initial stages. If this is a 1 minus cluster, this is 1 minus cluster, they come together, it should become 2 minus. Can you see 2 minus? Yes, it is 2 minus here. How do you know it is 2 minus? Because this mass that you measure is not really mass, m by z. Z is charge. Charge is 2, then the separation between the peaks is 0.5. 1 by 2. 0.5 is what the separation should be, and this is what you see. Now we thought that this fellow, which is the dimer, then atom exchanges, and all these peaks are a result of atom exchange, is what we thought. Well, there are so many peaks here. But you see, there are other peaks here, 149, 347, and all these peaks in between also. We did not pay much attention at that time when we published that paper. And I'm going to tell you something little more about these. Okay, so this cluster come together, they interact. When they interact, the interaction distances are something like this. And at that kind of distance, atom exchange become possible. We ask the question, which chemical bond breaks first and all that, which gives us mechanisms. But I'm taking you to something else. So here is a cluster, silver 25. We add a little bit of gold 25, and you get this equilibrium distribution due to certain kind of atom exchange. This equilibrium, you add a little more gold 25, you get another distribution. You add a little more gold 25, some more distribution. So it is possible that every atom in that cluster can be changed, and you can actually take it all the way there. Which means that from here, you should be taking all the way down here. So every atom in an atomically precise cluster can be substituted one at a time, and you can build very many alloy clusters. I told you that middle peak, something unusual that is happening. So we studied that in great detail. So here is gold 25 and silver 25 reacting to give you that dimer. And these peaks come as a result of that dimer. And so 0.25 is that peak, 124 that you see is this peak. But in between this peak, there is another peak here. which I put a star earlier, you know what is this? This is because this guy and this guy form a dimer. Which means that this guy, which is the one substituted product, there is a two substituted product, they also should form a dimer. So they form a dimer too. The 3 and the initial one, they should form a dimer. Yes, they do. So if you start thinking about it, so many dimers appear and they decay, and finally the system gets into an equilibrium with so many substitutions, and in fact 1760 chemical reactions happen in that solution. Oh, can you map all that? Yes, we can map all that. You see, here is 25, which comes down in intensity, but 24 AU comes up and then decreases in intensity. 23 AU2 comes up and decreases in intensity. This one, that one. So many others come up and decrease in intensity, and finally an equilibrium is obtained. And this is what you call as consecutive reactions in chemical equilibrium. So chemical equilibrium evolves in atomically precise clusters over a series of chemistry. So you ask this question, can I model it? Can I write a kinetic model? Yes, of course I can write a kinetic model. Can I predict it? Yes, I can predict. Can I get a kinetic rate constant? Yes, I can get. Can I get an activation barrier? Yes, I can. So very many interesting things happen. Well, I'm going to close this reaction because I need to use this rest of the time for something else. But I'm going to close it by saying that imagine you have this solution, gold 25, silver 25, coming and reacting. Now, but this gold 25, imagine it to be pure. This gold 25 molecule that is moving around in the solution will hit upon another gold 25, and there one gold and another gold can exchange. Is it not? Yes, it should be possible. Like water moving around, one water molecule, another water molecule should exchange. How can I know that this happens? Well, in the case of gold, it is difficult because gold has only one isotope. But in the case of silver, there are two isotopes. Silver 107, I told you, silver 109. I can buy both of these from Aldrich as silver metal. And I can come back to the laboratory and make silver chloride with 107 and 109. From that, I can make silver 44, silver 25, and all that I can make. So I made silver 25, 107, silver 29, 105, and then this is a pure compound. This is a pure compound. I told you that it has silver 109 and a ligand. Why is that there are so many peaks here? These so many peaks, I told you, is because of isotopes. Silver has only one isotope in this particular thing. However, sulfur has 4 isotopes, 32, 33, 34, and 36 in some ratio. Carbon has 2 isotopes, 12 and 13. Hydrogen has 2 isotopes, 1 and 2. So if you put all that in a statistical fashion, you can compute that, and that is the isotopic distribution that you can measure. Okay, here also some isotopic distribution is there, but the peak of this is 5192, and this is 5142. The difference between this is 50. And that 50 is because of 25 silver atoms. Okay, so that's great. Now, if I mix this and this together, suddenly, what should happen? Like H2O and D2O, you mix it together, you should get HDO. Yes, indeed. H2O and D2O, you mix it together, boom. Really, boom. This is what happens in just under 1 minute. So atom exchange occurs in solution, and this tells you that this system is highly dynamic. Now, there are very many other things that we have done in reaction. I told you one kind of chemistry, but this reaction can be also done, well, supramolecularly. So here is Nonappa in the audience, will show you more of these great many supramolecular assemblies. So here is a cluster. That cluster can assemble to form other structures. But cluster can assemble over this nanostructure called a nanorod and give you structures, and you wonder, how do you know this? How is this assembly? Yeah, well, you can do microscopy. So fantastic microscopy he will show you, well, with which you can see all these in great detail. Now, why are we interested in it? Because they can create the materials with properties of this and properties of this combined. So they are called hybrid materials. So why is that we are doing all this? We do all these because we can study chemistry in great detail. So when you study chemistry in great detail, you can use it for application. So about 20 years ago, 22 years ago, I thought that why not we use nanomaterials for clean water? So people told me, never do it. People told me, never do it, because if you do it, you may not get a name. Because nanoparticles, nanotechnology should be used for electronics, medicine, magnetism, storage, all that. So my grand applications were turned down. I thought, well, I should do it. Because there is a need for doing it, I was convinced about it. So we did our first patent, and that became a commercial success. So we got 2.5 crores of royalty to IIT Madras just for that patent. So that was my very first patent. Many, many things happened subsequently. Point is, you can study chemistry between a nanoparticle and a molecule or a cluster or whatever, which I told you the cluster now. Imagine you study nanoparticles such as some complex oxide and look at it to remove an ion from water or a molecule from water. Imagine this molecule is a pesticide. Imagine this molecule is arsenic, ion is arsenic. So you can find interesting thing. So we create complex materials to remove contaminants from water to create clean water. So this paper I don't have time to go through. Essential summary is that you create complex materials and filter water. But one other variant of this material we made, which is iron oxyhydroxide, and this material was made in the form of a tiny cartridge, and you attach it to water containing iron and arsenic, and you pass it through, you get clean water. So you ask this question, well, if you have arsenic of 3 plus and 5 plus, combined concentration of 200 parts per billion of arsenic, you pass it through this filter containing these 12 grams of material, you remove arsenic completely under 2 parts per billion. The limit of arsenic in water is 10 parts per billion. And it is possible that there are very many other materials available which can remove arsenic 5 plus effectively. It cannot effectively remove 3 plus. Okay? Can your new material remove 3 plus and 5 plus simultaneously with less contact time? Yes, you can do that. And with this material, you can remove arsenic from about 1,200 liters of water. That means it is possible to implement it in the form of a filter. When arsenic-contaminated water is present in the state of West Bengal, I can then implement it in schools. Then you can implement it in places such as these, which are communities. So these are community purifiers. So there are these kinds of community purifiers in a typical village in Punjab. So there are today 1,700 community installations across the country. Okay, so that's all great. So very many related technologies can be developed if you are interested in nanomaterials for clean water. So we have developed several materials, several products have come out, and a review summarizes all that. So if you have all these contaminants, how do you know? Detect them. You can detect it with a device, an electrochemical device, similar to a device that measures your blood glucose level. So it is a 3-electrode cell, and you can measure arsenic-specific sensing, like glucose-specific sensing is possible. Now, how do people do? People do that with arsenic-specific proteins called arsenite oxidase. So this arsenite is going to arsenate, and in that process, 2 electrons come out, which can be detected. This protein is sitting on the surface. But this guy is doing very good, but it cannot detect concentrations below 25 parts per billion. So arsenic limit is 10 parts per billion. So it is not possible. And I worked with colleagues in these places. They are masters of this technology. So atomically precise clusters, in addition to all that mass and all that, they have luminescence, I showed you. So these clusters can be put into reverse osmosis membranes, or different kinds of nanomembranes and other membranes, which Rahul Nair here is a great expert. So all these membranes you can make. So you can get this luminescence. You can do electrospinning, is another process that this is something that many people practice. Using these tiny fibers, you can create a membrane. These tiny fibers can contain clusters, and the luminescence is coming from these clusters. Clusters are very reactive, I told you. Is it possible that these clusters can detect metals in water like mercury? Yes, they can detect metals in water. How many ions can you detect? Just 9 ions of mercury you can detect. And we can enhance this detection using nanostructures like these that we develop, put clusters on top of it. These clusters which are luminescent, and they change color when mercury is present. So with Thomas Besset in this audience, we did something wonderful. That is, we used his molecules, which are called carboranes, and you put them on clusters. And these clusters are very interesting new materials today. You can make crystals. This is one such beautiful molecule that we made. Now, what is so exciting about it? So exciting that these clusters are extremely stable, and even up to about 300 degrees centigrade. Typically, these clusters are metastable materials, and they decompose at high temperatures. But here is something which is stable even up to this kind of temperature. That in solution also it is stable. So what does it mean? It means that real-life applications become possible. So here we have created a cluster. It is optical absorption spectrum. This is not noble metal cluster. It is containing cobalt and sulfur. They can be electrosprayed, and you can create interesting structures by a girl who comes from Kozhikode. So she's doing a PhD with me. So these clusters can detect arsenic right from water up to this 3.75 ppb. Here is a peak. So you can go even up to 1 ppb, can be immediately detected. And this peak intensity is proportional to concentration. It is selective to arsenite, as you can see, arsenate. So all different kinds of arsenite at various concentration that has been measured. It is not sensitive to any of these. So it is possible. Well, why is it doing that? This is doing because of some interesting electron energy levels, which I will have no time to tell you. But such clusters, you can make electrodes, and you can, in IIT, we have so many fellows interested in devices. So we make a small, tiny potentiostat, and that can be put in my pocket. I showed it to your minister, that this kind of thing can be done, and this device can be attached to an electrode composed of these clusters, and you can, arsenic detection, the data can be collected on a mobile phone. So my mobile phone collects it. So what does it mean? This data goes up to cloud. So I can put this data across. Well, there are very many sensors that we are currently deploying, but arsenic sensors can be deployed. Now, these are the regions where arsenic is present. In India, we are monitoring metal concentration, pH, chlorine, and bacteria, and all that across the country. And we participate in that national effort. And with that data, every minute we get water quality. But it is possible. Today, it is not possible to be done for arsenic because there is no sensor available. But it is possible to be done across the world. These are all regions affected by arsenic. The size of that particular ball or the circle that represents the concentrations in these different regions. So all these regions are affected. And if these regions are affected, and if there is an effective sensor available, it should be possible to address arsenic contamination. The previous data I showed you, previous slides, I showed you that an effective solution is available today. The solution that I told you is the world's cheapest solution, world's most sustainable solution according to World Bank. So therefore, they have funded that in these implementations. Now, it is possible that atomically precise clusters can measure these concentrations. So a kid goes to the field and measures arsenic concentration and writes that to the government that here there is arsenic concentration. Then the government can say, hey, go and implement that technology. So you can provide clean water. And that is our dream, to have metal-free water, contaminant-free water for the world. And this effort is possible only with collaborations. So I have people across the world with whom we collaborate. Several of you, you will see here, this person is here, and this person is here. Many others were there with me in Bangalore, but it is, of course, this team can expand further. This science is done by students. And it was supported by Department of Science and Technology. Thank you very much. I have 5 minutes for questions. Thank you.
Thank you very much, sir.
They are so close. They exchange all 25 atoms, but they don't exchange a single ligand.
No, they do.
Okay.
They do exchange, but we have carefully kept that ligand the same, so mass spectrum does not see that ligand exchange.
Okay.
But with other ligands, A has one ligand, B has another ligand. We studied all that in great detail.
Okay.
Yeah. Yeah.
Small clusters? Smaller clusters.
When we put them together, it is possible that pieces can come out and we detect them.
Yeah, great.
Yeah.
That's all.
When you pass water and that drop down to zero, close to zero, and after 800, 900, there is a step.
Yes.
Right? So this is actually per hour, or is it continuous passage, or what is that, the volume you are talking about, the exact?
Yeah, so that is, we are measuring it over several liters. So there is a constant flow that is happening through that filter.
Okay.
So every minute or hour or whatever, you can continuously measure it.
Okay.
Up to 1,000 liters, it removes arsenic. 1,200 liters, it goes above 15 ppb. So this is essentially what is called saturation absorption. Adsorption has occurred in these materials. You can do this at different flow rates to study different kinetics. So all those studies can be done.
After that, we have to remove the
So
material?
after that, so the material got saturated now. So you can now regenerate it. So this was the initial thought that we had, to regenerate, but regeneration produces liquids. Liquid discharge is a problem. Managing this in the field is a problem. So this material has to be taken to the factory and it has to be sent back, etc. So eventually, this is not the right way, we realized, particularly with arsenic. So we realized that wise thing is to do is improve the capacity.
Oh, okay.
So that 6 times, 10 times you reactivate, well, the effective capacity is much larger than that.
All right.
So we do that today, and our materials are the most highest arsenite absorbing materials today. So there is no regeneration that is there. Ultimately, there is this arsenic-laden waste. So what do you do? It's toxic. So now, nation has adopted disposal policies. So this is now disposed of in safe disposal sites. This is one way of doing it, but we also improved upon that to say that our materials do not leach arsenic at all, at the natural whatever conditions. So this is called toxicity characteristic leaching protocols we develop. We test that, and our materials do not leach. This is important because field is not having just arsenic. They can contain uranium. So in our course of our experiments, we found that there is a lot of regions having uranium. So we have addressed those, which are now at getting some media, Rajya Sabha, Lok Sabha attention. So this is now possible that advanced materials which do not leach these toxic contaminants can be developed.
The second question, in your gold 25 cluster, you add one silver. Can you trap each species? Is it possible you can have?
So each equilibrium,
Yes.
there is a distribution around that equilibrium. It's not just one thing, a distribution is there. A one atom substituted thing, a little bit of 2 and 3 will come.
Yeah.
So this, you can isolate it.
Oh, very nice.
Now, we can isolate. We have isolated several. One of them we have crystallized, so all that. Yeah. Thomas.
Oh, brilliant talk. Thank you very much, Pradeep. I enjoyed it. I have one question about the metal clusters. If you produce films using electrospray deposition, to what extent can we expect the film to be consisting of the original clusters? And to what extent do you think there might be changes which will actually give the film new kind of properties compared to the initial starting clusters?
Absolutely. So we've chosen such clusters which do not change. And we characterize those clusters in this film by optical absorption and luminescence. However, it is also possible that you can do a mixture and create a new thing there on that, which we have not done. That is indeed feasible. We can also create a mixture of such things, a composite such things. So ultimately, in the field, you want a real property. You are not worried about whether it is 1 cluster or 2 clusters or 10 clusters. So that means that it is possible to have several metal ions can be simultaneously detected.
Thank you.
Yes.
You made this cluster chemistry so interesting. I just want to ask you, these clusters have magic numbers.
Yes.
When many of those clusters you have seen shown, every cluster has a magic number. Is there any chemistry behind it, or is there any rationalization that if you do this, you get this cluster? If you don't do this, you don't get this cluster kind of.
So two aspects I should tell you. What these clusters are, there is a magic number because of a structural stability. There is also electronic stability. Both have magic numbers. There are structurally stable magic number clusters, electronically stable magic number clusters. Today we understand this, and both of them we have made. Now, do you have a rationalized synthetic strategy from 25 to 29 to 30 to 38, whatever? We do not have. So we have now mixtures. We have now recipes with which sambar or avial can be made, but exactly what makes it, we do not know. We have
Any theoretical prediction? Anybody is trying to look at
Yes, so there are some correlations like metal to ligand ratios, concentration, temperature, kinetics, all of those things exist, but they are not, not rationalized.
There's a lot of space there.
There's a lot of space, right. A lot of space there. Shalina, you should induce students to ask questions. I have brought one chocolate. One chocolate to begin with. Shalina has multiple. Chocolate is small. Okay, yes, great. Very nice.
Sir, thank you for the wonderful talk. I have 2 questions. First question is, you have used gold nanoparticles or nanomaterials for water purification. So isn't it expensive?
Yeah, very good. Fantastic. So I showed you gold, silver, etc. chemistry to tell you that all these can be studied in great detail. But what you use in the field are materials which are sufficiently cheap. They contain iron. They contain very ordinary rust, iron oxide, very common material. But they are having advanced, they have nanostructures. So they have interesting properties. We can talk about that, how do you induce interesting properties in a mundane, ordinary material. This is what we do. Coming to this, sensors, in some of the sensors we use this kind of expensive things, but there the amount that is used is so tiny. The amount of gold that is used in an electrode is costing less than 1 rupee. So you can do that. Okay?
Thank you, sir.
Thank you.
Another question is, you have shown the formation of some dimers.
Yes.
So what is the basic interaction that exists between these kind of dimers?
Beautiful. So those interactions are van der Waals to begin with. So later on, all these things come together with van der Waals interactions, and later on, they have covalent interactions.
So they will be stable.
They will be stable, yes.
Thank you, sir.
Can close it? Yeah.
Sir, I have one question. You have shown clusters with stabilized by.
Close it, bring it closer, yeah.
You have shown clusters which are stabilized by small hydrocarbons like methyl and aromatic hydrocarbons only. So how the stabilizing interactions between the ligands, small ligands, heavier ligands, how the stabilizing interaction between the ligands and the clusters is different when it is small like methane and heavier like aromatic feed.
So stabilizing interaction as far as this particular cluster is concerned is gold and sulfur interaction. That is covalent. But there are several other clusters with gold and phosphorus, cobalt and phosphorus, with nitrogen, with carbon. Diverse interactions make the clusters stable. This is about the cluster hydrocarbon interface or a metal hydrocarbon interface. That is, you can choose the chemistry appropriately. Okay? No. We can close it now. Yes. Yeah. You can use the mic there.
Okay, thank you very much. Nice presentation, sir. And I hope all the students have so many questions. You can interact with him during tea time and lunch. Thank you, sir. Here is a token of love from Farook College.